This novel approach integrates renormalization group theory with graph neural networks to enhance their performance on graph-related tasks. By leveraging the strengths of renormalization group theory in studying complex systems, a new graph rewiring method is devised for graph neural networks. This fusion of theoretical foundations and structural capabilities aims to improve the potential of graph neural networks in modeling and unraveling complexities inherent in diverse systems. The proposed method is supported by extensive experiments on standard benchmarks and baselines, demonstrating its effectiveness in remedying current limitations of graph neural networks. By combining the multiscale analysis of renormalization group theory with the structural representation capabilities of graph neural networks, this approach enables the modeling of complex systems at multiple scales. The experiments showcase the improved performance of the proposed method on various graph-related tasks, including node classification, graph classification, and graph regression. The results demonstrate the potential of this approach to overcome current limitations of graph neural networks, such as their inability to capture long-range dependencies and hierarchical structures. This integration of renormalization group theory and graph neural networks offers a promising direction for advancing the field of graph learning, enabling the development of more robust and accurate models for complex systems. Graph neural networks, GNNs, are powerful tools for analyzing complex data structures, such as graphs and networks. They have shown promising results in various applications, including computer vision, natural language processing, and recommendation systems. However, GNNs face challenges when dealing with large-scale graphs due to oversmoothing and oversquashing issues. To address these limitations, researchers have turned to renormalization group (RG) theory, a concept borrowed from theoretical physics. RG theory is used to study phase transitions and critical phenomena in statistical physics. It involves a series of transformations that gradually simplify the system while preserving its essential properties. The application of RG theory to GNNs is novel and groundbreaking. By applying RG transformations to GNNs, researchers aim to improve their performance on large-scale graphs. This involves coarsening the graph structure and adjusting the network parameters accordingly. The goal is to capture long-range dependencies and reduce oversmoothing and oversquashing effects. The paper presents several contributions to the field of GNNs. Firstly, it introduces the concept of RG theory in GNNs, providing a theoretical framework for understanding how these transformations can enhance network performance. Secondly, it proposes a new algorithm that applies RG theory to GNNs, allowing for efficient processing of large-scale graphs. Finally, the paper presents experimental results demonstrating the effectiveness of the proposed approach. The experimental results show significant improvements in GNN performance on various benchmark datasets. The proposed RG-GNN model outperforms state-of-the-art models in terms of accuracy and efficiency. These findings suggest that incorporating RG theory into GNNs can lead to more robust and scalable models capable of handling complex graph-structured data. In conclusion, the paper presents a novel approach to enhancing graph neural networks using renormalization group theory. By applying RG transformations to GNNs, researchers can improve their performance on large-scale graphs and capture long-range dependencies more effectively. The proposed RG-GNN model has shown promising results and opens up new avenues for future research in this area. The refinement process begins directly with the content, focusing on the renormalization of an unweighted graph. It starts by defining the Laplacian matrix and introducing the concept of neighborhoods, limited to undirected graphs. The discussion then shifts to graph neural networks, GNNs, highlighting the message passing paradigm and various update functions, including convolutional and attentional ones. The real space decimation process is detailed, specifically information diffusion in networks and the computation of diffusion trajectories. The authors introduce a method to identify nodes that reciprocally process the same information, defined as nodes where the sum of diffusion trajectories between them is greater than or equal to the sum of autodiffusion trajectories of one of the nodes. This is formalized in equation 10, where ρ ij is the ratio of the diffusion trajectory between nodes I and j to the minimum of their autodiffusion trajectories. The metagraph zeta is then defined in equation 11,
where zeta ij is equal to 1 if nodes I and j belong to the same supernode, and 0 otherwise. The decimation procedure involves substituting each cluster of nodes with a single supernode, whose edges are all the edges of the original constituent nodes that go outside the cluster. This results in a decimated graph composed of supernodes W, where ZW is the set of nodes in the original graph that compose the supernode W, and MW is the neighborhood of W in the decimated graph. The authors then discuss how to update the graph neural network, GNN, on the decimated graph, proposing an alternative to Laplacian renormalization group, LRG, that treats the decimation procedure as a rewiring process. This involves rewriting the update function in equations 14 and 15, where the features of the supernodes are functions of the features of their constituent original nodes. The authors then introduce their rewiring method, which identifies clusters that form the supernodes of the decimated graph and increases the number of edges by requiring all nodes in the same cluster to share the same incoming and outgoing edges. This is achieved by computing a new adjacency matrix * operator in equations 16 and 17, resulting in a rewired graph with a different set of neighborhoods. The neighborhood of a node U in the rewired graph is given by equation 18, which combines the nodes in the same cluster with the nodes in the neighborhood of the supernode. The research paper discusses the experimental setup and datasets used for testing the proposed graph neural network, GNN, model. A novel approach is introduced to improve the scalability of GNNs by simplifying complex graphs into smaller structures without losing essential information. This is evaluated on 4 datasets: Quora, PubMed, CiteSeer, and Amazon Photo. Each dataset represents a unique citation network or Copperchase graph with varying numbers of nodes, edges, and classes. The Quora dataset contains 2,708 scientific publications classified into 7 classes, with a citation network of 5,429 links. The PubMed dataset includes 19,717 scientific publications related to diabetes, classified into 3 classes, with a citation network of 44,338 links. The CiteSeer dataset encompasses 3,327 scientific publications classified into 6 classes, with a citation network of 4,732 links. The Amazon Photo dataset is a subset of the Amazon Copperchase graph, containing 7,650 products with 119,043 edges. The paper highlights the importance of the proposed rewiring procedure, which allows the GNN to act as if it were looking at the decimated graph obtained through the local ratio graph, LRG, when computing a node representation. This is established through Theorem 2.1, demonstrating the equivalence between the GNN update function on the rewired graph and the decimated graph. This means that the features of the original nodes are not saved in a different vector associated with the supernode, avoiding oversquashing. Instead, the features are implicitly represented by functions of the features of the original nodes, with some parameters learnable, allowing for task-dependent renormalization. The authors describe a graph-based product recommendation system where each product is represented by a bag of words encoding of its reviews. Edges are formed based on the "also bought" feature on Amazon. The graph encoder used is a 2-layer architecture, specifically graph convolutional networks, GCN, and graph attention networks, GAT. These are modified to create 2 configurations, dual and mono. In the mono setting, a single graph is input into the network, while in the dual setting, 2 graphs are fed into the network, one renormalized and one unchanged, to encode graphs at different scales. The model is trained using categorical cross-entropy loss, Atom optimizer, and a standard learning rate of 0.0001 over 200 epochs. The authors compare their method against graph diffusion convolution, GDC, which substitutes the adjacency matrix with a sparsified version obtained through a generalized diffusion process on graphs. They consider 2 diffusion processes, personalized PageRank, PPR, and heat kernel diffusion, and evaluate their method on the task of node classification using the accuracy metric. Experimental results are presented on 4 popular benchmarks, comparing 6 different methodologies, including the vanilla method, heat, PPR, and the author's own methodology with varying scales, tau.
The results demonstrate the superiority of the author's method across all datasets, with the Cora dataset showing the largest nominal markup. The optimal scale, tau, varies across different datasets, consistent with the theory of Laplacian regularization graphs, LRG. Graph neural networks, or GNNs, have revolutionized the field of graph data analysis, but they still struggle with infinities that arise from small-scale descriptions. Inspired by quantum electrodynamics, this research proposes a novel methodology that employs a renormalization group approach to remove these infinities and enhance the ability of GNNs to capture complex relationships and dependencies among nodes and edges. The proposed method is compared to popular GNN models such as Graph Convolutional Network, GraphSage, and GATT on 4 benchmark datasets: CiteSeer, Quora, Photo, and PubMed. The results show a significant lift in performance, reaching up to 12.1%, demonstrating the value of the proposed methodology and its potential impact on various fields involving graph data. The study also explores the effect of different timescales on the performance of the proposed methodology. It is observed that the best performing timescale value varies depending on the dataset under consideration, and larger timescale values tend to hinder the performance of heat and PPR methodologies. This raises important questions about the intricate connection between the timescale and its dependence on specific datasets and tasks, which will be addressed in future studies. This research provides a comprehensive overview of related works in GNNs, including their applications in node classification, link prediction, and graph generation. It highlights the importance of GNNs in transforming various fields that involve graph data and references surveys by Zhou et al. 2020. And Wu et al. 2020, for a broader perspective. The introduction of the renormalization group framework in the context of GNNs opens new avenues for research and improvement in the field. The research builds upon the work on continuous phase transitions by Wilson and Kogut, leveraging the Laplacian renormalization group, LRG, to overcome previous limitations. It focuses on undirected graphs with a single connected component, highlighting the need to consider weighted graphs and different aggregator types in future work. The method has the potential to alleviate GNN's limitations, such as underreaching and oversquashing, with applications in geometric deep learning and general deep learning. The research paper discusses the development of a novel algorithm for optimizing complex systems. It presents a mathematical framework for analyzing and improving system performance. The algorithm, based on dynamic programming principles, is designed to efficiently solve problems with multiple variables and constraints. The authors demonstrate its application in various fields, including logistics and resource allocation. The study highlights the algorithm's ability to outperform existing methods in terms of computational time and solution accuracy. Graph neural networks have garnered significant attention in recent research, with applications spanning various domains. A key focus is on the importance of ensembling graph attention networks for human microbe drug association prediction. This approach has been shown to enhance predictive accuracy and reliability, underscoring the need for careful evaluation of graph neural network performance. However, one major limitation of these networks is the phenomenon of oversmoothing, which can lead to a loss of graph structure and information. This issue necessitates further investigation into its implications and potential mitigation strategies. Another critical aspect is the concept of oversquashing and bottlenecks on graphs, which can be understood via curvature. These factors can significantly impact the performance of graph neural networks, highlighting the importance of understanding and addressing them. Despite the progress made in this field, there remains a need for further research on graph neural networks. This includes addressing their limitations, improving their performance, and expanding their applications to tackle complex problems. By refining our understanding of these networks and their challenges, we can unlock their full potential and leverage them to solve real-world problems more effectively. The authors present an analytical result demonstrating the equivalence between computing the update function of a graph neural network, GNN, on a node of the rewired graph and computing a GNN update function on a node of the decimated graph. They begin by defining the decimated graph, which is composed of supernodes obtained by clustering the nodes of the original graph based on the zeta matrix. The neighborhood of a supernode W in the decimated graph is denoted by MW. The rewiring procedure is defined such that for each node U in the original graph, a neighborhood nu is created, which is the union of the set of nodes in the same supernode W as U and the nodes in the supernodes adjacent to W. The authors then state theorem A1, which shows that the update function of a message-passing GNN on a node U can be equivalently computed on a node W of the decimated graph. The update function is defined as who equals phi, shu, psi, shu, xv, for v in nu, where phi and psi are neural networks, and shu, xv are node features. The proof of the theorem is provided, considering the case where the aggregation function L is an average. The authors show that the update function who can be rewritten as who equals phi, xw, psi, xw, xv, for v in mw, where xw, xv are supernode features, and phi, psi are neural networks. The authors use the definition of the activation functions phi and psi to rewrite the update function who in terms of the weights and biases of the neural networks. They then define a new supernode feature xw, which is a function of shu and the features of the nodes in the same supernode as u. This allows them to express shu in terms of xw, and subsequently rewrite the update function who in terms of xw and the features of the adjacent supernodes. Overall, this result demonstrates the equivalence between computing the GNN update function on the rewired graph and the decimated graph, which has implications for the design of efficient GNN architectures. The authors of the research paper continue to derive equations for their proposed model in the final page. They introduce a new function, psi, xw, xv, as a transformation of the original function psi, shu, xv. This transformation allows them to rewrite the equation for the neural process as a function of xw and m, where m represents the set of indices in the input space C. The neural process, H, is redefined in terms of phi, psi, and xw, highlighting the learnable parameters in the model and demonstrating how these parameters can be optimized during training. The neural process, H, is now expressed as a function of xw, m, and psi, xw, xq, where xq represents another set of indices in the input space C. The paper concludes with a summary of the key findings and equations derived throughout the document. The proposed model offers a novel approach to understanding and modeling complex distributions over functions, leveraging the strengths of both neural networks and Gaussian processes. The equations provided offer a clear framework for implementing this model in practice, making it accessible to researchers and practitioners in the field of machine learning and artificial intelligence.